Okay, let's get started. Good morning, everyone. This morning we'll have 3 talks, and we'll be starting off with the first talk by Gil Holder from UIUC, and he'll be telling us about cosmology with the CMB beyond the power spectrum.
All right, well, nice to be here. So I'm going to talk, first I'll start with CMB lensing. And so there was some talk about that yesterday. So I think I added one slide just for some discussion, and perhaps we'll get derailed there and then maybe we won't finish anything else. We'll see what happens. Then I'll talk about Kinetic SZ as something we can do for helium reionization. So someone talked about helium reionization earlier, and I think it's just really exciting. It's a cool thing to try to measure. And then if I have time, I'll talk about the polarized Kinetic SZ as something to think about in my retirement. All right, so the cosmic microwave background has been really great for cosmology. We've learned a lot, and we've learned from the power spectrum. So here's the CMB power spectrum as of last year sometime. So what you see is that the temperature power spectrum is extremely well measured. There are actually error bars on all of these points, and they peter out at L of 3000. And the reason they petered out there is because that's where we're starting to hit foregrounds. And so it's very hard work to get past L of 3000 because you're starting to get into all the astrophysics that cosmologists try to avoid. There's the polarization power spectrum, the E modes. And what you see with the E modes is they're pretty well measured, but you can start to see error bars on this. And they peter out around the same spot, just mainly because we're just running out of signal and noise. And so there's a ton of information still in the microwave background by measuring these acoustic peaks out to L of maybe 5,000 or so. There's a ton of information there. There's actually as much information in the EE polarization that we have not yet measured than is in all of the TT that we have measured already. So there's lots to do with the power spectrum still. So I'm going to talk about beyond the power spectrum, but that's not to say there's nothing left in the power spectrum. It's just not what we're going to talk about today. Then you go down below the EE and you have the BB power spectrum. And what you see there is that we're just starting to measure the B modes. So these are the lensing B modes out here. And of course, what a lot of people are looking for is the hint of this inflationary B mode signal at very large scales. So there's lots to do with the power spectrum. So, but that's just not what we're going to talk about today. So we want to talk about these different experiments. So these things out here, this is SPT. This is something where I've spent a lot of time. Planck is mainly at lower L. So what does this look like in a map? So here's a map of the 143 gigahertz Planck sky zoomed in on some chunk. It's been filtered to match the SPT filtering, and then just to see like what we gain by going to a new experiment. You see this is the same patch of sky. You blink back and forth and you see there's just a lot more structure in general. So it really sharpens up all of those peaks. But then what you also see is you see a whole bunch of bright dots. And so those bright dots are a mix of either AGN or dusty galaxies. Most of the dusty galaxies in here would be strongly lensed. And then if you really squint, you see like a black dot like there. I don't know how the projector is for everyone. So that's a galaxy cluster. This is the Snežev-Zeldovich effect, which people used to think was hard to measure. You just see it right there, and you don't really see anything in that Planck map at this scale. So, there's lots of astrophysics and things like that, but there's also lots of CMB in this map. So that's what it means. Measuring the small scale structure in the CMB is just all this fine scale structure in the CMB. This is what you can do with high resolution, low noise. All right. So there is the SPT. It's at the South Pole. It's at the South Pole. We survey a bunch of the sky. Just to orient you, here's what we look at. So we have 1,500 square degrees. In this map, south is up. There's the South Pole. There's our patch, 1,500 square degrees. This thing in here is the bicep Keck patch. So we've chosen so these are the people that are looking for the B modes on large scales. We completely overlap with them, and that's by design, as I'll get to a little bit later. So then there's some numbers about our noise. So just the main thing to take away from this is that as of 2020, which is the data set we're doing right now, our noise levels are already deeper than what the Simons Observatory is going to get to. And by the time we're done the experiment, we'll be at roughly the temperature depth of CMB S4, but only over 1500 square degrees instead of over half the sky. All right. So this is a big data workshop. And I thought, big data, am I doing big data? It never occurred to me I was doing big data before. Because, you know, there's the power spectrum. That's like a few thousand numbers, right? That's not big data. So that's a few thousand numbers. And it's like, oh, but we have a map. But then you say a map, so that's not even a billion numbers in there, right? So we're still not like big data, right? That's something I could load into my phone and do some manipulations with. So how does CMB even end up as big data and data processing? Well, it's because the way we make these maps is by just relentless observing of the sky over and over and over again. And to give you a sense of what that means, so this map, this right here is a coad of 1 year of data. From SPT, and you see there are the point sources, and you can see the background fuzz, or at least the people in the front row can see there's just some haze in here. That's the CMB, so that's a year of data. This is 2 hours of data. And this is another 2 hours of data. And you can see even in this 2 hours of data, some of the little haze in here is actually coming out as in this background here. So in 2 hours of data, we can actually image the CMB at the level you can start to see it by eye. And then you can see why it's useful to be doing things over and over and over again. So in fact, there's a dot in this one that's not in here, and this is a stellar flare that just turned on for 10 minutes and then disappeared. And so we're not quite sure what's going on with those, but this is something that we figured out. So that's 2 hours, and you say, okay, well, still, that's 2 hours, so still you do it for a few years, that's still not that much data. But to make this map, this has about 15,000 detectors that are reading out at about 150 hertz. So you start to put this together, and what we generate is about 300 gigabytes a day. So to make, you know, so these red dots up here, there's, I don't know, maybe 100 of these red dots are coming from 300 gigabytes a day over something like 2 years. So it actually is a fairly substantial data volume. Like, we can't do it on our phones anymore. And then you go up to the next generation or 2 generations, CMB S4. So instead of 15,000 detectors, they're going to have 500,000 detectors. And so that's a big hit. And so you do that scaling and you're getting a data generation rate that's comparable to LSST. So there is some data coming. There's a lot of data that has to get processed. And there's just this fire hose that you have to keep up with. It's a lot of data. So the reason we're going at 150 hertz is just because we're scanning across the sky. So you scan at a degree per second at arc minute resolution, you've got to read out. So CMB S4 will have that same readout. So this is big data. So I did this exercise. Okay, I belong in the workshop. All right, so what would you do with these maps? So you can do the power spectrum, but my title said I was going to go beyond the power spectrum. So why would you want to go beyond the power spectrum? So here's just, I took a chunk of the Planck map. I pointed at Polaris. So here's, you know, Polaris is at the center of this map. So this is the North Pole as seen by Planck. And then just for an exercise, I just stuck a gravitational lens in here. So this is the before, and now I'm going to lens it. And you're going to see if you can see it. It's pretty obvious, right? So you see there's a lens over here. And so it's like, oh, okay, well, there's obviously a lens right here. And now you have to think about how you would reconstruct this lens. So what is this lens doing? And so you look at it and you say, well, this spot looks different than the rest of this map, but it's not a mean. The mean's not different. But what you see is just the characteristic spacing of the patterns is larger here than it is here. And that's because it's just this big spot of convergence. We just magnified the sky. And so effectively the power spectrum is shifted to larger scales over here than it is there. And then you see out here, something else has happened. You're like, oh, okay, well, that looks like everything's kind of sideways. So what we've done is we've taken that power spectrum and it's now been sheared out. So now it's anisotropic. It's stretched out in the vertical direction over here and the horizontal direction over there. And then out here, you see it's gone back to where it was. There's no lensing going on. So what this is this compensated profile where I put in some constant density thing with something underneath it. But so now you think about how you would reconstruct this. You would say, well, it's something to do with the power spectrum. So there's something about the variance as a function of scale. And that's anisotropic here. And so what you're talking about is a 2-point estimate that's spatially variant. So it's just locally changed the statistics. It's still Gaussian at each one of these points. It's just the statistics are no longer the same as what they were before. So the way you would reconstruct this would be to construct some estimate that's looking at the power spectrum or the variance, which is a 2-point function. So that's why you would look for this with what's known as a quadratic estimator. You need the square of the map and look at how the square of the map is spatially varying and look at how that has some anisotropy to it. So that's the quadratic estimator. So this is in the temperature. The same thing will happen in the polarization. All right, so we ran a quadratic estimator. So we've done this for generations now. It's been 15 years or something of this. And so we've made a lensing map. So let's just skip ahead to our lensing map. So here's the lensing map from the SPT data. And this is just our 2019-2020 data. You see this big red spot here, and this is why this is currently ongoing. So that's a quasar that got through our point source masking, so we're gonna have to fix that. So that's a lensing map. And so we did this, but lots of other people have done this. So here's the Planck map. So Planck has done it over the whole sky. And just to give you a sense of what the difference is by having SPT, so I'm gonna replace the center of the Planck map. So if you look at this map, most of this by eye is actually noise. Planck map is signal noise, just barely better than 1. So the SPT map has substantially higher, so you just go back and forth. What we've done is we've just kind of smoothed out a lot of the noise in the center here. So a lot of the structure is still there, but we've gotten rid of some of the noise. So what does that look like? In a plot like this, so here's the angular power spectrum of the lensing map. So there's the Planck lensing map. So this is the signal. The Planck noise looks something like this. So ACT just put out a big release. So their noise is substantially better than Planck. So this is, something like a factor of 3 or 4. So it's 2 times lower noise. And then the map I just showed you, the noise in that map is another factor of 2 below that. So you can see that as the CMB maps are getting better, the CMB lensing maps are getting better, and we're just pushing down in noise. So with the SPT reconstruction, there's actually a group of 4 people that are kind of leading the charge. So this is my student, Kale, who's at UIUC. Marius Malaya is at Berkeley, Yuki is at Chicago, and Kimi Wu at Stanford is doing a lot of this work. And we're actually doing it 3 different ways, because this is actually, it sounds easy. You just look for the power spectrum spatially varying, but it's harder than it looks. So we actually have 3 different ways we're going at it. One is doing sort of a flat sky, where we're just dividing the sky into chunks and making sure that everything makes sense, running a quadratic estimator. We're trying to do a curved sky, where we do everything in heel picks. And then Marius is leading this Bayesian version, which is actually just doing a Bayesian fit to a joint solve for what is the unlensed CMB and what is the lensing potential, which is, it sounds very hard and it's complicated, but it works. All right. So what have we lost? Okay. All right. So let's skip over this just so I can get to the rest of my talk. So there's a talk yesterday. So yesterday in the discussion, there was someone showed, well, I think it was some version of this plot, maybe. I'm not sure, but there was discussion about how well CMB lensing does compared to cosmic shear. And so, it's not, so if you go back in time, so the first ACT release was 2016 when they did, well, at least the most recent one before the last one. So if you just plot sigma 8 versus omega m, and so here's the SPT version that we did in 2019, sigma 8 versus omega m. What do you see? So here are the various lensing surveys of the time. There are the Planck constraints from just the power spectrum. These are 2 different SPT versions. This one is SPT pole, and the previous generation was more sky, but less sensitive, and that's SPT SZ. So there are the SPT results. And you see, they're a little bit fatter than the shear results. So, in a different angle, but, not grossly different. And then you look at, so here are the ACT results from 2016, and you see, again, there are the shear results. And then you see the CMB lensing is there, and then the Planck lensing is in there. And in this one, the Planck lensing is right here. And so now we just go forward in time, and you see a plot like this, and you say, and this is the ACT lensing, and you go, wow, CMB lensing got so much better. But if you look in this 2016 ACT paper, you see actually, if even there, this was the sigma 8 omega m right here. sigma 8 omega m. So that's this thing right here. If you put a BAO prior on that, that tightens this up substantially. So a lot of the tightening here is coming from the combination with BAO. And so that's what this is. This is ACT plus BAO. ACT on its own is this very thin thing in the outside. And then here is, what is this? DES on its own is out there. And then you add BAO there. And it tightens it up, but not as much. But you see, like on its own, DES and ACT are not so different. So I felt like there was maybe a little bit of a freak out going on, like, oh my God, we've been doing all this lensing and the CMB lensing is just 100 times better. It's not, it's just that the BAO is more orthogonal to the CMB lensing than it is to the shear. So please keep doing shear. All right. So this is the SPT constraints from 2019. So with the generation that we're working on right now, that map I just showed you, when we do a sigma 8 omega m constraint from that, we should get something that's roughly 2 times tighter than that, which will be very close to what the ACT is. It'll be at the level of your eye, you won't be able to really tell which is which. And then we'll see where we are. All right, so we can come back to this if people have questions. I know there were lots of questions about that before. All right, so there's a power spectrum, right. So, so here's the B modes right here. So the reason that SPT overlaps with bicep Keck is specifically to look at these B modes. So these are the lensing B modes, which is to say these B modes get generated by taking the CMB polarization and lensing it. So with that map I showed you, we can actually undeflect the CMB and then make a B mode map that will be clearer. So here's from, schematically how this works is you have lensing B modes that come from lensing of the E modes. If you have a lensing map, you can undeflect that map, make a new B mode power spectrum, and that should move the lensing noise down by whatever fraction you can do that delensing. And if you can do that, then you should get a cleaner look at these gravitational wave B modes, which is to say you reduce the sample variance on small scale, at low L by knocking down the lensing B modes. And so this, you only need to do this if you have noise that's below 5 micro-K arc minute. And that's right where we are with SPT. So bicep Keck is well below that even. So right now, this is actually what's limiting bicep Keck. So, so we've banded together bicep Keck with SPT. We've called it the South Pole Observatory. So when you see pictures of the bicep Keck experiment, often SPT is in the background. So they're co-located at the South Pole. And what this plot is how well you could measure the gravitational waves as a function of time. And so this is bicep Keck is up here. And if they didn't do any delensing, they would basically be stuck no matter how much they added to their experiment at a level just below 10 to the minus 2 in their sigma of R. If there was no lensing at all, you could see they'd be almost they'd be basically a factor of 10 more powerful. So the lensing is actually completely limiting how well we can measure R with bicep Keck by a factor of 10. If you add SPT, you see we can knock this down by a factor of something like 3. So, so that's what we're doing. There's an ongoing, and again, we have the different pipelines for doing this. And the goal is to just clean up the bicep Keck constraints on R by a factor of something like 3. So that's the plan. All right, so, but that's 2 point, I guess that snuck in there. All right, so now we have some time to talk about something else we can do beyond the 2 point. So let's talk about the kinetic Sunyaev-Zeldovich effect. So here's a cartoon. I love cartoons. So imagine you have a bunch of galaxies that are just out in space. And now I'm going to have them caught up in a bulk flow that's all moving towards me. So all these things are coming towards me. So, okay, fine. Now I'm going to put a little cloud of electrons around them all because, everything that has large scale structure around it, it has like a little 1 halo term and a 2 halo term. So every galaxy is correlated with electrons. And now I'm going to add the CMB. So the CMB comes in from all directions. When it scatters off these things, it acts like a moving mirror. It sort of upscatters things in the direction over here. So an observer over here looks at these galaxies, and everywhere where I see one of those galaxies, I'm going to see a little tiny excess of CMB photons. So it's going to be a little bit hotter at the locations of those galaxies than at locations where there's no galaxy. And if I look over on the other side, I'm going to see at every location in the sky where there's one of these galaxies, I'm going to see a slight hole in the sky. It's going to be a little colder on one if it's moving away from me and a little hotter if it's moving towards me. And so what that says is that if I just do a cross correlation between the galaxy map and my CMB map, that's going to tell me what that velocity is, right? So the cross correlation between the CMB map and those galaxies, as I look at it, the amplitude of that is just telling me the velocity. If it's coming towards me, it's going to be some positive number. If it's going away from me, it's going to be a negative number. The faster it's moving, the bigger that's going to be. So, so what we have is a way to estimate velocities just by doing a cross correlation between the CMB and galaxies. So there it is. So if you want to do it in math, you look at what the amplitude of the KSZ is proportional to. It's going to be proportional to, well, a Thomson cross-section, how much hydrogen is, but this thing right here is this electron fraction. So that's why, so there's an electron fraction. You need to know how many electrons there are per baryon. And then you also need to know what the correlation is between galaxies and electrons. So there's a thing that comes into that's going to be the power spectrum, the cross power spectrum of galaxies and electrons, which is to say, how do electrons trace galaxies? So you do that cross correlation, you construct the velocities, you get some noise, and so that's the power spectrum, 1 over the power spectrum of the noise. And that's going to be, you measure a velocity given some known relation between galaxies and electrons and a known electron fraction. But you can turn this around and you can say, well, what if I could reconstruct the velocity in some other way? Then maybe I could learn something about either that or that. So this is what people, so this is something you can do. And you say, well, how could I reconstruct the velocity? Well, I could use a galaxy survey. So someone talked about that yesterday, reconstructing velocities with from galaxy surveys. We could just use the density to do a velocity reconstruction. And when we do that, what that says is that we'll actually know what this velocity is. So if we actually know what the velocity is, and then when we do that cross correlation, this one right here, that cross correlation is telling us about these electron clouds, which is both their distribution or the overall number of electrons per galaxy. All right, so why would that be interesting? Well, so one application of this would be, you could say, where do electrons come from? It's kind of like a question a kid would ask, I guess. Mommy, where do electrons come from? So let's see. So the universe was neutral before hydrogen reionization. When the first galaxies form, you send out a bunch of UV. That UV knocks an electron off of the hydrogen. It also knocks an electron off the helium. But helium's got that second electron, which needs a harder radiation field. And we don't think that stars are going to provide enough hard radiation to be able to knock that second electron out until you get enough quasars. So, so what we get is we get helium reionization, which is happening probably between redshift of 3 and 4, because that's when you have enough quasars to fill the universe with enough hard UV to knock that second electron off. So at this point right here, we're suddenly going to get an extra electron per hydrogen or per helium. And so what that means is that if I do that velocity reconstruction for things at redshift 5, helium still has that electron. If I do it at redshift 3, helium's lost it, which means there should be some transition that happens between a redshift of 3 and 5, where we get extra electrons per galaxy. So, so you can turn the crank and say, okay, well, let's just put in some specs for maybe something like, LSST plus CMB S4, and say, well, how well could we measure this? So let's say that we just had a galaxy catalog, and we had a CMB map, and we're just going to reconstruct the velocities with the galaxies, and then we're going to do the also reconstruct velocities by doing that cross correlation between the CMB and the galaxies. And then we're just going to compare those two velocity estimates, and the amplitude difference between those two is telling us the electron fraction. And so you look at how well we can constrain helium reionization. What you see is actually, you can tell that helium got reionized. You see that it'll go from some transition in here So the constraints are bad out here just because we don't have enough galaxies. The constraints get better here because we have a lot more galaxies to work with. And you can see we go through this transition, and these are 3 different models for helium reionization that were run by Paul LaPlante. And you see we can actually tell the difference between exactly how helium got reionized. And then you go run the clock forward to some more futuristic ideas for a galaxy survey of MegaMapper or CMB-HD, and you see we can actually really start to map out this transition. So kind of a fun thing we can do. But notice that we're well beyond the 2-point function, right? We're doing the galaxy reconstruction, and then we're doing the galaxies cross CMB. So that's 1 point in the CMB and 2 points in the galaxy distribution. That's a 3-point function. But this is something that's not that far off. So this is with VRO plus S4. Oh, I thought you said I had 5 minutes. Okay, that's fine. So what would you do with that? Well, so one thing you could do with it is you could actually measure the helium abundance. So what you find here is how well we could measure the helium abundance. This band right here is roughly how well we know the helium abundance now. So you can actually measure the helium abundance in a way that's competitive with what you can do nearby with just H2 regions around in dwarf galaxies, which is one of the ways we constrain BBN. So this gives us a new handle on BBN. All right, so let's see. So we'll skip the polarized. So there's a polarized KSE, which we're not going to talk about, and I'll just leave that up here. So hopefully what you got out of this was that CMB lensing maps are coming soon. They're going to be pretty sensitive. They're going to be the best CMB lensing maps around. They're actually going to be comparable in signal noise to a lot of the shear maps. So I think they'll be kind of similar in signal noise per pixel compared to the DES maps. They should be close. We'll see. And then this KSE tomography is something that's coming. So I think you're going to see a lot of it in the next few years. So it's emerging as a new cosmological tool, and I think we could think about things to do with it. So I showed helium reionization. There's probably lots of other things you can do. And then I didn't talk about polarized KSE. That's it.
Questions? Okay.
So for the plot you showed with the VRO plus CMB S4, the helium reionization, so can you actually do like a velocity reconstruction with like the photoz's of?
Well, this is very large scales. So these are bulk flows that are, so photoz's are good enough for these scales. We're talking about, hundreds of megaparsecs. So these are the very large bulk flows. You're only getting a few of them along the line of sight. So they should be good enough. Obviously, spec-z's would be better.
More questions?
I was looking forward to hearing what kind of survey will be needed for polarized KSZ, but you skipped. Do you mind?
So the polarized KSZ is really hard. So you're measuring a kinematic quadrupole. So what happens is you have a cloud of electrons. If you're moving relative to the CMB, you see the dipole as V over C, and then you see a quadrupole as V squared over C. And so that kinematic quadrupole is a V squared over C. So you do V squared over C, you calculate how big that is, and it works out to be a few microkelvin, maybe 10-ish microkelvin. So it is a small piece of the quadrupole that we see in the CMB is just from our motion. But it's small. And so let's see. So what we found is that even with CMB S4, that measuring this in cross correlation with galaxies would be something like 2 sigma. And so what that says is that with SPT, we have sort of similar noise, but we don't have enough sky to build up the statistics. And so with CMB-HD, and so I didn't talk about what CMB-HD is, but that's something like well below 1 micro-K arc minute. So, so that's going to be tough. So to measure the polarized KSE, you need to get, oh, right. So we can finish the thought. So so you get a few micro-K is the quadrupole. And then you say, it's KSZ, which means you're going to scatter that, which means you can multiply that by the optical depth. So you start with a few micro K, and then you multiply it by the optical depth per thing. And for a galaxy, a typical optical depth is about 10 to the minus 3. So you go from a few micro K to 10 to the minus 3 times a few micro K. So you're starting to get into the word nano K, which you don't hear very often. And so that's tough. But if you could do it, it's pretty cool because you know, you're actually measuring velocities of things. Like you see things moving on the sky and you can actually measure their velocities from their polarization. It's worth trying. It's just going to be hard.
I was curious, like if you can scale up the galaxy survey and stack more of those things and have also 3D velocity, let's say if we have good enough reconstruction, yeah, will that not help, or is it completely dominated by CMB noise?
So this is dominated by, so let's see. So the calculation we did was dominated by CMB noise. So if you had a fully dense survey, would you be able to do this? So if you had like the full map of the universe in full resolution. Yeah, so it was definitely true that we were not impacted by the noise and the shot noise in the galaxy survey when we did the calculation. So that's true. So it means that we are limited by the CMB for this measurement.
Yeah, just a quick question about the CMB lensing constraints you expect from SPT. So I think you said you expect something similar to ACT, but then I think you also showed a plot where the lensing noise for SPT is considerably better than ACT. So
because we only have 1500 square degrees.
So it's the area that's causing the difference.
Yeah, so it's just the area.
Okay, thanks.
One last question.
Hi, thanks for the really good talk. So there was a measurement of, since you mentioned birefringence in your last slide, there was a measurement of that from the Planck data recently. Is there any effort to follow that up from SPT?
Well, we're not actively pursuing it because it's a global polarization measurement. So for one, like we don't measure. So what they did is they measured. So the problem is if you're trying to measure birefringence, you're trying to measure rotation of a polarization angle, and you have to know what it's been rotated from. And so that means you need to have an absolute polarization angle, so you know exactly which way is up. And so you can try to calibrate your experiment as well as you can, but it's really hard to know exactly which way is up. So what they did for the Planck analysis, so what they did is they said, well, we're going to use the galaxy to calibrate which way is up. And the way they did that is they assumed effectively that the galaxy doesn't have any EB correlation, that there's no relation between the curl-free stuff and the stuff with a curl. Because if it's just, you know, a bunch of random star-forming galaxies, bunches, like, how could that do anything strange? And so they calibrated with that, and they said, okay, well, we're going to make sure that there's no EB correlation in the galaxy, and then look off, and then say, well, then we see some net rotation, so we're going to attribute that to birefringence built up as the CMB propagated through the universe. So, well, with SPT, we don't have the galaxy. So we only have 1500 square degrees for our main survey. So we're actually mainly not looking at the galaxy. So we could look at the galaxy. We're now looking a little bit at the galaxy, but I mean, personally, that just seems like a huge leap to just assume that there's no EB correlation in our galaxy. So what you'd really want to do is just come up with a really good absolute calibration of your polarization angles. And so the people that are trying to do that, what they're talking about doing are things like flying drones with a known calibration angle, or building some calibration station. So I think, who is doing this? I think maybe it's ACT is actually, or SO I think is actually putting in a calibrator at some distance. But we can't do that with SPT because our far field is too far away. So just the optics of SPT means that we can't put something within a few kilometers that would actually be seeing, where we'd be seeing it in the same way that we see the sky. So we wouldn't be able to trust that calibration well enough to be able to do that transfer with SPT. So who could do it is Bicep Keck or anyone that has a small aperture telescope. So there are people that are doing it, just not us.
All right, let's thank Gil again.